Welcome. All right, welcome back to Easy Math with Nick. This is video number 2, and today we'll be finding center of mass and more, which we'll get to, with calculus. So starting off here, I have this image of a question that I pulled up here that we'll be tackling today. This is not my question. To make that clear, this is from College Board. I do not own this question, so do not come after me. So this question states, I'll read, a wedge of mass m is balanced about its center with a small cylinder of mass m attached to its narrow stem. The cylinder part doesn't matter that much. But the linear mass per length of the wedge can be modeled by equation of the form lambda equals bx squared, where b is a constant with appropriate units and x is the distance from the narrowest end. And our question here is, what is the ratio of the masses of the two objects? So there's a lot of layers to this question for a simple multiple choice question. They're given 2 minutes to solve. They ask a lot of you here. Just reading the question took a minute. So good luck doing this in time. Just joking. We'll unpeel the layers of this onion step by step. So let's start with how do we solve mathematically for center of mass? So in physics class, if we have multiple objects along a line like this, just a single one-dimensional, well, technically two-dimensional plane here. No, we really only care about one dimension. X equals 1 meter, whatever units here. We just have some point masses here. I'll try to keep this video mostly math related, but there's going to be a little bit of physics here. But the math part is really where it gets fun here. I would say these are both mass 2m, 2m. This is the mass m. So if we have objects organized like this, how we find our center of mass introduces like that idea, XCOM, COM, center of mass, just to be clear, introduces the idea of like a weighted average. So we're going to have x1, m1. This is just a general equation. I'll get to what I just drew in a moment. m2 plus ... Our final object, x sub n, m sub n, and divided by the total mass, which is going to be m1 plus m2 plus ellipses plus m sub n. So that's the equation you see in algebra-based physics class to find center of mass, and it's sufficient. Gets the job done, and it could also be expressed as, if we want to use summation notation, using the sigma here, I'll just use k equals 1 to n of xi mi divided by, if you just have the total mass, you don't even need to use sigma down here, but mi. So this is how you will see center of mass indicated. So for our example up here, the center of mass would be, let's find that, x1 times m1. I'm sorry, let's undo that. Just no, m plus x2 is position 2 times 2m times position 3 meters. And what's its mass? 2m. Divided by the total mass, which is m plus 2m plus 2m, 5m. So we're going to have 1m plus 4m plus 6m, 11m, 11 over 5. So at x equals 11 over 5, which is going to be somewhere like right here, there's going to be our center of mass. So let's just say over 5 equals x comp. So that's just a visual representation of this center of mass equation. But as we said today, we're going to be using calculus. So how do we introduce calculus to finding the center of mass? Well, let's say we don't have 3 nice objects here like this. Let's say we have the classic wedge that I think they're showing the example. Yeah, a wedge, a triangle that looks like this. Now, there's no discrete objects here. It's one continuous wedge. So how do you find the center of mass of this wedge? Well, you have to be given some information, of course, but if we're going from discrete objects to a continuous object, that sort of indicates that we're going to be wanting to integrate, because we're adding infinitely many little mass wedges of position x and mass dm, which indicates a very tiny mass. So if we want to add all those up, instead of, so that's going to be without limits here, without including the collector elements. I'll get to that in a moment. We're going to be adding up, all these little mass wedges here until we get to the end. And if you see, this parallels our equation up there, because on the bottom here we're going to have integral of dm. because we wanted the center of mass. This just gives us the sum of all these little mass wedges with respect to this location here, with respect to location. But um, we want to find the center of mass. So that's why we need this dm over here, because this is just, it's not going to guess the right units unless we have this. So expressing this with the correct units, we're going to have just an example I'll provide here. It depends on the scenario, of course, but x equals 0 to x equals L. So this is the definition of center mass when we start to think about integration and how to find the center of mass of a continuous object. And take note here that it is not x dx, x dm. So the main question now, we're going to start off by solving this question here is, how do we find dm? How do we do that? So for this question, the reason why we need to use calculus to find the ratio of the objects, the masses of the two objects, without even getting into too much physics here, is because this wedge has a force of gravity acting at its center of gravity. So we need to find where its center of mass. It's gonna have a force of gravity acting at its center of mass. So we need to find that center of mass to solve this question. That's why I thought this question had I said it had a lot of layers. I was not lying. So they give you what's known as the linear mass per length of the wedge, which is expressed as dl over dm equals lambda, which they said here was bx squared. So this is very convenient because dl is equivalent to saying dx, because it's a change in length, whatever we want to indicate that as. So that dx is going to equal lambda times mass differential, which is going to yield dx equals bx, let me see if I, yes. Oh, my apologies. It's dm over dl. Boop, 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 boop. I could edit this part out, but it's good to know that I can make mistakes as well. I knew that didn't sound right. Because of lambda. Multiplying the length differential over, we'll get dm. We were solving for dm, not dl. I don't know what I was thinking. Bx squared times dx. And so now we get something nice that we could substitute back into our original equation to find center of mass up there. So let's do this. Okay. So integral, what we could solve the denominator right now. So if we have x equals 0 to x equals L dm. This is just a fancy way of saying what's our total mass. So the total mass of the wedge is mass m. So we already have m. So mass m. And then we have the integral at the top here. This is almost reminiscent of the average value function that you might have learned in your calculus class, which is definitely not a nice coincidence. It's intentional. And now let's worry about the top. So we have this expression for dm up here. I'll use a different. We have this expression for dm, and so we're going to bring that down here when we swap over to we're just going to bring it down here. I'm not going to say anything else. Bx squared dx. I don't know why I add parentheses, just for clarity. So if we pull that b out, we do not need that b. Do not need that constant b. It's a constant, so you can just bring it out. We don't need to keep it in the integral. I'm going to keep my limits. We don't need to express the limits in terms of x anymore. We get, it's implied, so we'll just have 0 to L of x cubed dx. So this is sort of getting sloppy here, so let me bring it here. So we're going to have b over m. This is just to find center of mass, by the way. I should be saying that all along. b over m, 1/4 x fourth. This is just a simple calculus question now, 0 to L. So that's going to yield us b over m times equals x com. B over m times, I thought that was an x for a second, 1/4 L to the fourth. Oops. L to the fourth. And finally, this is going to get us b L to the fourth over 4m. And so this is going to be our center of mass, if I'm not mistaken. Yes, so that that b, that constant b there, we'll make sure that this has the correct units. So you might be thinking, wait, we have mass in the denominator. Aren't we supposed to get rid of mass? We want a unit of length, like meters. Yes, but I think that has to do with the constant that we defined for b up here. So without confusing ourselves too much here, let's just ignore that part. Let me see if I'm doing this right so far. Okay. Continuing on, now that we have the center of mass using calculus, it's time for step 2. So this is the most physics part of it. As we saw in the original question, this wedge is balanced around its center. So that means that this wedge is in static equilibrium, which means it's not the net torque, the net forces on it are going to cancel out. So it's not accelerating, it's not moving, staying still. So in the physics way, we express as net torque equals 0. And we have to look at the torque being caused by both the cylinder or whatever the object at the end here, and that and the torque being applied by the gravity at the center of mass here. So I thought this was getting a little bit too much into physics for me. This is supposed to be a math video, but couldn't help myself. So let's do it. So for the wedge itself, it's going to be the force of gravity is going to be acting at center of mass. So the force due to gravity here is mg, and its center of mass is acting at bl to the fourth over 4m. And this, let's make sure we have the correct sign here. It's sort of hard to visualize, but because we don't know exactly what b is. I'm thinking we don't want b, but I think it's fine. We're going to have to add one to the other side anyway. To keep it balanced, they're going to have to be in different directions anyway, so I don't think it really matters for this sake. Without getting too much into physics, I apologize. And then that other cylinder has mass small m, so its gravity is represented by mg, and it's at the very end of the cylinder there, so it's a distance 1/2 L from the center. But our problem here is this. Let me just take a second here to look over what we've done thus far. It's my first time recording this. I think we've been doing this correct so far. I don't see anything wrong. All right, I think what we can also do is put b in terms of something else, because that b is bothering me. So we could also, because lambda equals bx squared, if x is equal to L, bl squared is going to equal, that's the total length of this rod, of this wedge, my apologies. And so because lambda is dm over dl, we could express lambda as m over L, because it's the total mass over the length. That's another way to express lambda when we're looking at the total object. So I'm sorry, we're solving for b, not for m. So we use. So b is going to be equal to m over L to the power of 3. And so this does actually, in reality, help us a lot. This is more important because now we can substitute this up here. So let's just do that before evaluating the expression for torque I had. So we're going to have m L cubed times L over 4 divided by 4m. And so this cancels quite nicely, and then the m's cancel. So we're going to have L over 4. That is quite wonderful. So finally, we can actually solve this question. So if we do net torque equals 0, which just means that this object is staying at rest, without getting too much into the physics part of this, L over 4 is our center of mass. L. And now we add that to the other side and divide by g, because g is a constant, just to clarify that it's gravitational constant. Note that we want, we could also divide by L as well, but I'll take it one step at a time. 1/4 m L. So now let's divide by L on both sides. 1/2 m equals 1/4 big M. Now multiply both sides by 4. We're going to get 2m equals m. And the original question wanted the ratio between big M and little m. So the mass of the big object compared to that of the cylinder. So m over m is equal to 2. And let's check up here. And our answer is 2. Quite wonderful. I ain't even look. So that took a while. A little bit too much physics, in my opinion, even though I do like physics. We just had to include that notion of net torque equaling 0. Which just means very simply that this object is not moving. And the gravity that this cylinder exerts has to counteract that of the center of mass of the wedge, which is going to be, like we said, at 1/4. So this is going to make, this wants, the gravity of the wedge wants it to go counterclockwise, but the cylinder wants to make the rod go clockwise. So that's why it's able to stay at rest, because it keeps it nice and even. And because we don't take this into account for other reasons, but but quite simply, that's why, that's all that's going on there, to keep it very brief. And so I think that's about it. That was a good question. I had to take a pause there because none of the options had B in their answer. So you had to put B, you had to solve for B and then substitute that in. That's a real tricky part of the question you don't see often. But I think that's it. A little more hesitation and perhaps would be ideal. But I feel for a first attempt of this problem, I think we did a pretty good job. So thank you for watching. This one was a little bit of a longer video. But thank you.